Hello everyone, and welcome to this session. So first, who we are. I'm here with Marc and Thibault, and Loic is there in the room too. We founded Spin42 about 10 years ago. It's a software consultancy company. And in 2016, Loic started playing with Elixir by trying to build, and succeeded to build, a quadcopter running on a Raspberry Pi with nerves. And based on that experience, we decided to build our next project, which was an open banking aggregator with Elixir 2. It was a success, and we could sold it to a bigger company. And since beginning of this year, we are enjoying a little sabbatical time. And for that time, we wanted to play with new things and learn as much as possible. And then we thought, why not playing with a car? It's embedded. It has a lot of things to think about. So why is the automotive world interesting to us? It's because it's quite a closed world. The manufacturers do not provide any documentation, and the average lifespan of a car is quite small compared to what most of the components could be used. So what's also weird to us is that you cannot really mix components from different brands. While, for example, the throttle pedal of your car is just a potentiometer that is measuring a resistor, and it's the same in all brands, but you cannot use a Nissan throttle pedal in a Volkswagen. Which leads us to OVCS, which stands for Open Vehicle Control System, and it's meant to be a set of open source software and hardware components, and that would allow you to extend your car, retrofit it, and also prototype new features for a much lower price than what you would expect in the automotive world today. And as developers, we also hope it will be more developer-friendly than what you can find usually. In our specific case, we are doing this on a 207 Polo Blue Motion and a Nissan Leaf 2013 electrical motor. So we try to convert that vehicle into an electric one, and it's a car that has a story because it was the first car of Marc, which then sold it to Loic as his first car too, and now it's back into the company, so it's kind of fun. Little disclaimer: don't try this at home, or at least do it at your own risk. It's open source, but it hasn't been certified or tested on the road yet, so you've been warned. The design choices, so the goal was to build something that could be used or tested by as much people as possible. So we are using Raspberry Pi Force boards, deployed with nerves for the Elixir code. And we also have a few Arduino boards running the interaction with the analog parts of this old card, because not everything runs with on the network of the car. Then these boards are not automotive grade, so we might have to revisit the choice if we really want to build a product with that. Then on the software level, we are coming from the web app world, and we wanted to see how far we could go with all the tooling and the nice, the nice frameworks we have to build web applications. So we decided to build the front ends in Vue.js. Then we have Phoenix apps providing APIs and WebSockets through Phoenix channels. And behind we have standard OTP apps running the Elixir code that's doing the business logic behind. So in this case, you have the throttle pedal example where, since we want to be able to use any throttle pedal on the market, we have a calibration phase where from the interface you start the calibration, and then we store the resistor value for 0 and 1% of the gas pedal when you push on it. And then from there, you could use any pedal. Here is a schematic of the big picture of the system. So in blue, you have the OVCS components, which are the components we are building ourselves on the Arduino and Raspberry Pi 4 boards. And it's connected to its own network. So you have the vehicle management system that is connected to all the networks of the car. And then in OVCS, you have also the Arduino boards that are activating the contactors to enable the high voltage for the motor and so on. And then the infotainment is basically the touchscreen we are putting in the old car, so that you have something nice to display the information and the entertainment part. Then in green you have the Volkswagen legacy part. So most of the car is there, and we are trying to keep as much as possible so that we don't have to buy anything. And in yellow you have the Nissan Leaf part with the motor, the inverter, and the charger. And finally, we have bought a new battery management system. The good part is that then when you buy something new, you have the documentation, which means it's easier to use and it's probably safer to handle the battery. So you see what I mean. Let's dig deeper into the vehicle management system. So as I said, it's really the car brain. It's deployed with nerves on a Raspberry Pi. And it's the one connected to all the networks, and it's translating the messages, because you have legacy messages from the Volkswagen for the RPM that has to be sent to the Nissan part and vice versa. So if you really want to see everything working together, you need to do this translation. And as you can see in the scaffold we have 3D printed, you have 3 Raspberry Pis. Today we only use one, but the goal is to have some hardware redundancy so that if it crashes, even if it shouldn't, you don't crash the car itself. Hopefully. On top of that, we also have a monitoring interface on that VMS. So it's a bit small, but it's a real-time interface using the channels of Phoenix to display the values returned by the car network. So you have the gas pedal throttle applied, the torque which is applied to the motor, the temperatures, the RPM, the voltage, and of course the speed. It's also displaying alerts when one of the boards is down or not emitting the messages as expected, which help a lot to debug what's happening. And then it's also there that you configure the car. So for example, the calibration I've talked about. This didn't come without challenges, of course. Testing our hardware, it's much more complicated. We are coming from a web application world where you have all this tooling, you can mock everything. So we are trying to do the same, and then you work at home, you build your little component, then you come back to the garage, you put it in the car, and then you have wires, you have interferences, you have all this sort of things, which makes it a bit more complicated. And then same for the 3D printing. You have this nice design, you print it for a few hours, and then you try to put the Raspberry Pi in it. It's a bit too short. And then you fix it, you have to wait a few more hours to see if you actually fixed it, which can be a bit more frustrating, let's say. And then also the network of the car, it's named a CAN. And we were missing in Erlang an Elixir, a library that is still maintained. There are a few, but not really maintained, and not providing all the things we needed. To go a bit deeper into the CAN, CAN stands for Controller Area Network, and it's a bus that is designed to work in a complicated environment like a car where you have a lot of electrical interferences. And it's connecting all the components, and that's really standard in all cars, trains, planes, and so on. It's nice because it's standard, it's even part of the Linux kernel, but while the network itself is standard, the messages and so the frames that are sent and the data are not. And of course, the car manufacturers are not providing the documentation, which means that we had to spend quite some time reverse engineering. So on the video, you can see the software that we use to reverse engineer the bus. And so you connect on it, and then you see the list of messages with their IDs. And then you have the raw data in hexadecimal, and the color changes when the content of the byte changes. So how it works is basically Marc was in the car, I was in front of the screen, and then Marc was pulling the handbrake, and I was trying to see which frame was changing to what value. It's a bit tedious, but in the end, there is no encryption or whatever. It's just really the raw data, but it's not structured like a JSON where you have a key and a value. It's just a set of bytes, and you have to find what kind of endianness and whatever they use to encode it. It's also quite different than working with a REST API, because it's a bus where all the components are continuously broadcasting their status, and then you have to subscribe to whatever is interesting for you. Based on all this experience, we have built an open source library, which is fantastic. It's still alpha, but it's available on GitHub and XPM. So if you want to play with your car, again, at your own risk. It's based on a YAML file. You define the frames and where to look for values, and then you can easily subscribe in a Gen server, for example, and you will receive messages with the interpreted value in your business logic. So, for example, here we have the ABS, which is sending the speed, and we can see here that the speed is actually an integer starting at bit 8 until bit 16, and that you have to multiply it by 0.0075 to get the value in kilometers per hour. We should ask Volkswagen why they apply that scale.
We have ideas, but yeah.
Still not clear. So yeah, it took a bit of time to find that scale. And then in your Gen server, you just subscribe to it, you receive the value in kilometers per hour, and then your own code is quite simple because we do all the complicated logic in Fantastic. On the other way, if you want to emit frames, sorry. Here we have an example about in the OVCS network. We select the gear on the screen, and then we have to send it to the vehicle management system. And so we decided that we would just map an integer from 0, 1, 2, 3 to drive, neutral, reverse, and parking. And we then have emitters, which are basically Gen servers that the Fantastic is spawning, and then it's continuously emitting the value at the predefined frequency in the YAML file, and then you can easily update the value in the state of that Gen server.
All right, so another set of components that Thibault talked about are the controllers, or the things that we basically use to enhance existing features of the cars, to extend it with CAN capabilities. Here you can see the original gas pedal of the Polo, literally on a wooden board, connected to an Arduino, and then on the right of the picture you see the low fidelity gear selector that we implemented in our prototype, which basically allows us to select the gear, so P, R, and D for now. So these are just 4 buttons on an Arduino, and so it connects to the CAN network through the serial peripheral interface of the Arduino. Using a simple MCP 2515. We're not going to go into details of this, but it basically is a very dumb logic component that just sends data continuously about its state through the CAN network. And then it's captured by the vehicle management system through Fantastic so that we can do something with the data. Sorry about that. So we did this for the analog gas pedal, I would say. We also have controllers to activate the relays that will deliver the power to the motor, actually. So because we need to have pre-charge and then all sorts of actions happening before we can drive the engine. And we also plan to do this to continue seamlessly integrating features into the old car, meaning that for now, for instance, on the dashboard of the Polo, the fuel gauge is just a potentiometer, basically. And so it's not connected to the CAN network. So we're going to hook it up to an Arduino so that we can send it CAN messages and basically set the needle to the exact percentage of battery that you have left. So we really want to make it so that the retrofit, or at least with the modifications we do on the car, make it feel like it was always like this to begin with, that the car was made to be like this. So yeah, might be a bit crazy, but it's fun. Some challenges as well. Like we said, we want to work with off-the-shelf components, but it's not always great in the sense that in order to use relays, to activate the relays, we use the relay hat from Arduino. And what we noticed after hours and hours of trying to figure out what was wrong, we noticed that the relay hat actually uses a pin of the Arduino for a specific relay, and that same pin is actually used for the SPI interface. So you cannot use the SPI interface at the same time that you want to use the Arduino hat. So it means we had to literally bend the pin of the hat so that it would not connect to the Arduino, so only use 3 relays instead of 4, so that we could still plug our wire so that we could have the connection properly handled. So again, maybe it would not be like this if we were working with automotive-grade components, but for now, that's what we played around with. Another thing that we knew from the start, but still, we thought we knew better and we did it anyway, is work with the right kind of cables. Anybody doing hardware probably knows this. So in the beginning, we just wanted to go fast, so we used Ethernet cables instead of proper CAN cables, which were not properly insulated. So we had a lot of interferences as soon as we started plugging everything together and starting sending high voltages through the system. Same for USB. You would not imagine how many USB-C cables do not provide enough power for Arduinos or Raspberry Pis that need to really have the maximum power you need to make this happen. So yeah, all in all, it was sometimes few headaches because all the USB cables are black, right? So you can't really, or the ones we own at least. So we had to label them at some point, I would say, or to figure out which ones we could actually use for this project. So yeah, another next step for us might be to look into automotive-grade alternatives for Arduino. We don't know, we haven't looked into this yet, so if anybody is familiar with technology in this world, the automotive world, and you can recommend us something, let us know. Another component, optional component in itself, is the infotainment system, which is also connected to the new network we created, so the OVCS CAN, and also connected to the car drive CAN. It's currently running nerves in kiosk mode with WP WebKit. And we have a nice 3D printed enclosure that allows us to just slide it in the radio bay of the car. So we just basically have a new touchscreen for the car. So it's, again, Phoenix apps, Vue.js front end running on nerves. Just a quick demo of what it looks like. We actually ran a small scenario for you. So we had Loic open some doors of the car so that we could see it live. And you can see the handbrake is on right now. So now we're going to start the engine because we're using the original key to start the engine, meaning that in most retrofit, you're going to be providing the 12 volt or whatever standard is in your country to the car with the key, and then you need to actually have another button to start the electrical motor. So because we have all the CAN messages, we could actually use the original key of the car to trigger the relays for the motor. So again, we tried to make it look like the car was electric to begin with. And so we just lit the beams, and then the engine was ready, so we started to go for a drive after selecting the right gear. So gives you an idea of what we have today. The blocks at the bottom are not working. We haven't connected the batteries yet, and we still haven't worked on the multimedia system, I would say. We built a few screens also for debugging, where we show all of the data on the infotainment system. But yeah, that's pretty much it. So we're having fun also with this. It doesn't come out without challenges. Somehow, yeah, making it work in kiosk mode is not so easy. We ended up realizing that sometimes when there's a new build root version, our system doesn't compile anymore, or there's something that breaks and we have to figure out a new combination of components. The problem with this is that also WP WebKit, or at least the combination we're using, takes a lot of time to compile. So it takes about 30 minutes, 40 minutes to have the system compiled and testable, I would say, which on a new machine. So it's not that great at the moment, the life cycle. And we still have sometimes intermittent issues. If anybody is familiar with DRM, so direct rendering managers, we would have a few questions for you on Raspberry Pi, because it seems to be a bit random. Sometimes we get that, what we call our own blue screen of death, like the DRM device just doesn't start. So we don't really know why. We haven't had time enough to dig deep into this, but that's definitely an issue we want to try to fix. One thing we could try is to actually go for standard Debian that we would actually ship with live build, so something really custom for what we do. That would be an option, but we'd rather stick to nerves, honestly, for this. So we'll see what happens in the next weeks. So everything together, you've seen the slide, just to remind you of what we were working with. This is what it looks like from a mechanical perspective, I would say. So you can see the leaf motor connected to the original gearbox of the Polo. So obviously these pieces didn't fit together. So you have to build a connection piece between the two. Loic, being a welder by trade, well, not by trade, but by hobby, I would say. So he's a software engineer by trade. So anyway, Loic had to weld new motor supports on the chassis of the car so that we could fit it. And also you have 2 aluminum plates that were CNC cut to fit the exact blueprint of each piece, and then welded together in the middle. That's what you see, the piece in the middle with the arrow. And then on the picture on the right, what you see also is the junction piece between the engine, the motor, and the existing gearbox, because obviously these did not match either, so you have to create that piece as well. So it was also created from scratch. Also, because we didn't have batteries to start with, Loic also made us a really nice 330 volt DC power supply, which gave us a bit of a sweat the first time we actually started it. One of us was on the emergency switch of the garage, and we were like, what's going to go up? So we thought it would blow up, but it didn't, and now we keep using it, and we're much less stressed when we light it up. It's doesn't seem like much, but it's serious, serious voltage and current that goes through these things. So yeah, we don't want to fry playing around with nerves. All right, so this is our prototype board as it is today. So you see so you can see the vehicle management system on top. Then you can see the temporary gas pedal right next to it, and the rest of the gear selector as well. Then you can see some contactors, controllers, which are the ones that activate the relays that we need in order to power the motor. And of course, there's a lot of wires all over the place. All of this needs to be connected together and in a certain pattern, I would say. So the next step there is to make this in a size that fits in the car, in the engine bay somewhere, and obviously put the gas pedal where it belongs, which is not on this. So you can see it working. Some of you have seen parts of this on Twitter as well, maybe, but so what you see is wheels actually turning, going through all the components. So it means that somebody has selected the right gear on our controller, pressing the gas pedal. The motor is actually, giving torque to the wheels, and also the VMS is translating the messages from the Nissan Leaf motor, so the RPM messages, to messages that the Polo actually understands, so that we can show the RPMs. Because in a traditional retrofit, we would not have that needle moving; it would just be dead, flat dead. So that's really how you can see. Also, we have an oil problem. Anyway, so there's still a few things we need to figure out how to remove entirely. But yeah, so this is wheels turning. Obviously, the next step for us is putting the batteries in. So you can see we got the batteries 2 weeks ago, 3 weeks ago now. We have the battery management system and the batteries, so now we need to put them in, basically. So, and once that is in, we will drive the car out of the garage, because obviously right now we cannot do this with a big wire, so it would not be very convenient. So like Thibault said, we still need to add a lot of redundancy in the system, so especially on the vehicle management system, also on some of the controllers. We really need to go back and thinking again about the safety of all of these components before we want to drive this at high speed. Also use automotive grade components, and still we're looking a lot into this. Maybe one day it would be an autonomous vehicle. It would be pretty cool to do self-driving in Elixir in this car. So yeah, why not?
Will you let it crash?
Well, yeah, it's true. It gives a It gives a whole new dimension to the idea of let it crash. I agree. Well, the idea is We don't want to let it crash, obviously. So yeah, look, this closes what we had today for you. We wanted to leave time for questions. So we're leaving you with that video in a loop about all the mechanical work that Loic has been doing, mostly with his father. Because you know, removing an engine, you don't need to be three around it. But yeah, there's a lot of work that's been going on also on the mechanical side for this car. We also want to thank, well, Loic's father, Joël, and also Jean-Luc Delvaux, which helped us a lot on the electrical part, or at least mostly the power supply part. So yeah, look, I guess we have time for questions. We could not go into very much details about all of these things, but yeah, feel free to go for it.
I was just wondering if this means we would now have a future where you can do fun things like get the car up to 100 kilometers an hour and then put it in park.
You could try.
You have a very interesting definition of fun things. I would call it dangerous, not fun, but yeah, maybe you want to answer this one.
You could try. We would not probably.
You can still try. I think the engine also has its own protections for this. So we're not completely changing. So like we said, we got the motor. There's 3 layers to the motor, right? So there's the actual electrical motor, there's the inverter, and then there's the charger. And there's also all sorts of things happening in there. So it's just a black box receiving CAN messages. And so I don't think we can put it in reverse if we don't go to parking first, right? So
well, actually, an electrical motor, if you apply the reverse, which means negative torque, you will just slow down the car. So it will slow down the car with the power of the motor, and then it will go backward.
And in a way,
it should be okay.
For the motor, parking is just like neutral, right? So it's just stop applying any torque. So parking in a traditional car would mean, you know, pull some kind of hydraulic brakes or whatever, which is completely different. So in this case, you could potentially force it to go to parking, which I don't believe we can with the motor, but it would just be the same as putting it in neutral.
Yeah. We have 5 gears in reverse.
Yeah, 5 gears in reverse, because we kept the gearbox, so you could go 120 kilometers an hour in reverse. So that would be fun. That would be fun.
Electric cars usually don't have a gearbox.
No,
so if a car is intended to go in first gear at 150, if you put it on 5th gear at full RPM, how fast does it go?
We don't know yet.
As fast as forward, but you have to be able to.
Maybe the gearbox will break before we know. We don't know. We don't know.
There's a myth bust this episode, and it's not possible.
Yeah.
So I've played with nerves and trying to deal with sensors and like making sense of that raw data coming in is a nightmare. Did you have any tools or techniques that led to breakthroughs in what you were seeing or what you were understanding?
Well, so we used some sniffing software. Also, in the open banking aggregator we did before, we had to reverse engineer bank applications to be able to connect to their APIs, which gives us some experience in that. Of course, we spend quite a lot of time on Nissan Leaf forums, where you have lots of people that posted kind of part of the messages, which helps guiding you in the right direction.
And did you have any like particular techniques or visualization tools or anything like that from the software world that helped you?
Yeah, so the video we shown is SavvyCAN. It's an open source software to sniff the can. Yeah. And then you can graph the values and you can apply scale, so you can visually see if what you've, the transformation you apply to the raw data will match what you see on the dashboard, for example.
So it's like also the 0.0075. The intuition we have is that the anti-blocking brake system is actually a returning radian per second, and if you take a radius wheel, tire included of 35 centimeters, kinds of match this ratio. If you do trigonometry, it would actually match that 0.75, and it would mean that the sensor actually gives you radian per second to the second decimal shifted, so times 100, so that's why it's 0.0075. So that's the intuition we have, but we're not from the automotive world, so we don't know. So yeah, there's sometimes some things that you see that you have to figure out some way, one way or another.
Yeah.
But
the usual way to do it is you drive the car, you record the CAN, and you can even record the dashboard, and then you try to match the timestamp of the value and the value displayed on the dashboard, and then you do a mapping with a function. The problem was that we removed the motor of the car, and then we started thinking about how we will reverse. Oh, shoot.
So maybe we should have got a trace, a CAN trace before we removed the engine.
Some people are publishing traces on the internet, so we could still do that. Thank you.
All right, that's all we have time for questions. We have a brief break now. Our next talks will be at 3:40, and thank you so much.
No worries.
This has been great.
Thank you.